Welcome to this lesson on modeling and simulation with system analogs entitled The Encouraging Simulation, with the subtitle, How to Use the Electrical Analog of a Mechanical System. My name is Benjamin Bacon, and I will present this lesson to you. By the end of this lesson, you will understand why it is called the encouraging simulation. In previous lessons in this series about modeling mechanical systems with electrical analogs to those systems, I described the relationships upon which that process is based, and I applied the concepts taught to a specific mechanical system. There are still some additional lessons to be taught to cement that method into your catalog of engineering skills that can be applied to simulation and modeling tasks. In this lesson, I will complete the series by giving a complete example of the modeling and simulation process using analogous circuits. I will use the methods on the same system that I described before, and I hope that by the end of this lesson I will have given you a clear example of how the electrical analog is used for modeling and simulation of the mechanical system. I will use the simulation power of the LTSPICE electrical circuit simulator to help me achieve my objectives. The process begins with an LTSPICE model of the electrical circuit analog that was derived in the previous lessons. This is a baseline model for a spring mass system using flow variables. The mass flow system is represented by two variable capacitances, labeled here as C1 and C2. One of the inputs to the system is a mass flow between the two branches, represented by the variation in the capacitance values. Another input is the mutual force represented by the current source connecting the two capacitors. The motion of the system is modulated by the mass flow between the two capacitors. The mass variation is periodic and effects an instantaneous magnitude change. The mass of a component is represented by its capacitance value. In operation of the system, the mass instantly increases if the velocity, represented as voltage on a capacitor, is negative. The mass on the component, again represented by its capacitance, decreases instantaneously when the velocity of the component becomes positive. Thus, inertial bias becomes the method of modulation of the motion. The system accomplishes a motion that is biased toward positive velocity. The inductor, L1, represents a spring in the system model. As you will see by the end of this lesson, according to the LTSPICE simulations, this system will move almost 40 millimeters in 30 seconds. This is the mechanical system that is being simulated by its electrical equivalent model. The masses in this system are what were represented by capacitors in the electrical model. They are coaxially arranged along their longitudinal axis. They have the same mass until the inertial bias is added to either one of them. They exchange the inertial bias or mass using a mass transfer system. The masses are connected by a spring between them, represented by the inductor in the electrical system. Finally, there is a mutual force between them that is alternating in the same way that the current source is alternating in the electrical model. The mechanical system is the real-world system that is being simulated. The mechanical system is the one that is being designed, and the electrical model is the means by which its performance is being evaluated through simulation and modeling. Now, let's review the mechanical and electrical system equivalences. They are: mass is equivalent to capacitance. Velocity is equivalent to voltage. Acceleration is equivalent to the voltage rate of change. Mass transfer action is equivalent to a capacitance value changing when the polarity of the voltage on it changes. The spring is equivalent to the inductor, and the force generator has as its equivalent the current source. The mass transfer action is the inertial bias that modulates the motion in the system. It works by ensuring that the mass that has a negative velocity, that is going backwards in terms of the desired direction of motion, that mass instantly becomes twice its normal mass, thereby damping the reverse translation in the system. The mass that has a positive velocity is always half as massive as its counterpart, causing forward translation in the system to be amplified. The spring, with the spring constant value of 1, is the component that happens to make the system work better. It stores energy, and if used properly with the other components, it improves the system's ability to achieve forward translation. In the simulation, based upon this model, the mass ratio between the masses is always 2:1 or 1:2 from the perspective of either mass. The motion is constrained by structural methods to be along only one space axis. Returning to the electrical equivalent model, there is an interesting construct in this LTSPICE circuit model that merits some explanation. It is the expression Q equals X times if X is greater than 0, then 1, otherwise 2. This is a special nonlinear construct in the LTSPICE mathematical syntax that allows the modeling of nonlinear variable capacitors. The mass transfer action is thus modeled as a variable capacitor that doubles its capacitance value when the voltage on the capacitor becomes negative. To gain further understanding about these expressions, go to the documentation of LTSPICE, distributed freely by Linear Technologies. One of the inputs to the mechanical system is a force, which is modeled in the electrical equivalent circuit as a current source. The type of source that is used is a pulse. The driving force is a pulse going from 0 to 10 milliamps magnitude. The rise time and fall time of the pulse is 1 millisecond. It is a relatively slow changing pulse in the light of pulses that rise and fall in nanoseconds. The duration of the pulse is 998 milliseconds, with a repetition period of 1 second per pulse. The drive is operating at nearly 100% duty cycle. The entire pulse train operates for 30 seconds. In mechanical system terms, the pulse has a magnitude of 10 millinewtons if the system is considered to be modeled to scale. That magnitude of impulse propulsion is in the same range of the thrust that ion drives provide through electrical propulsion systems that use gas jet thrusters. The mechanical system modeled here falls in the same class as ion propulsion, in that it is a low-thrust electrical propulsion system if the force generator is electrical. This is the output that resulted from the simulation. It is a plot of the voltage on capacitor C1 and the voltage on capacitor C2 as time progresses. The voltage on C1, representing the velocity of mass 1 in the actual mechanical system, is the green plot. The voltage on C2 is the red plot. This output indicates that the simulation showed that the average velocity of the system of masses will be positive. It also shows that in the portion of time in which the voltage is negative, the output has less magnitude for each of the capacitors. The voltage only goes negative to a trough of 4 millivolt, while it goes positive to a peak of 8 millivolt. This translates into smaller average negative velocities for each mass and greater average positive velocity during the respective phases of their motion. This is what was desired and expected from the modeling and simulation process used here. Therefore, on average, after the mechanical system has operated for 30 seconds, with a 10 millinewton pulse train driving it, and with motion modulation by the mass transfer system, it should achieve an average velocity of 1.376 millimeter per second for mass 1 and 1.2206 millimeter per second for mass 2. Now, let's do the math to show just how useful the electrical equivalent modeling process can be. In the mechanical domain, where the voltage values now become velocity values, the system response to the drive can be calculated. Without any scaling being applied, millivolts become millimeters per second. Then acceleration can be calculated as velocity divided by time. Taking average velocities from the output and dividing them by the time duration of the simulation, 30 seconds, it is found that the average acceleration of the system is about 0.04 millimeter per second per second. The average acceleration of both masses is nearly the same, with a slightly higher acceleration on mass 1, since it had the positive velocity first. These results show that the system stays together and behaves as a unit. It is operating in a coherent mode of motion. The root mean square motion shows the same coherence in the motion of the two masses, as both of them have an average RMS acceleration of about 0.15 millimeter per second per second. Summarizing the simulation results, the RMS acceleration of 0.15244 millimeter per second is the same as a translation of 152 micron per second per second. After 30 seconds, a velocity of 4.5732 millimeter per second will be achieved by the system. That's about 0.0046 meter per second. These are small results, but in the context of electric propulsion systems, where the acceleration is applied continuously for a long period of time, this system will be a successful propulsion method. Applying the kinematic equations of motion to the results of the simulation, the picture is completed by indicating that the position change of mass 1 after 30 seconds will be 0.06858 meter. The position change of mass 2 after 30 seconds will be 0.06793 meter. They are both translated approximately the same distance in the same direction. This is the confirmation that the system moves unilaterally and exhibits coherent translation of the two masses. The final ingredient in the discussion is the spring. In the electrical system, it is modeled by the inductor. The inductance value assigned to it, 1 Henry, is equivalent to a spring constant of 1 Newton per meter. The function of the spring in the system is as an energy storage mechanism. However, its analysis is complex, and so the discussion of its details will not be included here. Suffice it to say that the results obtained without the spring in place are not as encouraging to the assessment of the feasibility of this system for propulsion use. Now, this series of lessons has reached its conclusion, and I hope that you have discovered why the simulations that were described to you are encouraging to me as a person interested in developing a propulsion system based upon the mechanical system I designed. Thank you for taking the time to view this effort of mine to try to explain the enigmatic topic of inertial propulsion to you. It is not easy to explain or understand. However, that did not stop us from trying. Please like this video and subscribe to this channel if you are pleased by watching this type of programming.